In this video, we're going to be reviewing the most important aspects of NMR spectroscopy and applying that to solving problems. Again, here we want to remember that if we have some, say, conceptual questions, we want to know some of the basics. In here, we remember that you need an odd number of either protons or neutrons or both. And here's some examples. And the one that we're using the most is proton NMR in carbon NMR. But we have also other possibilities. So here we have the characteristic of a spectrum. Here we have one more that we didn't do in IR. So which is the number of signals. So we're going to be determining how many signals, in this is in regards to types of H's or protons, right? And then characteristic of those signals. So where are they? So chemical shift, the area, the integration, and that has to do with how many H's give that particular signal. And the shape is a splitting pattern. So here at a glance you see 1, 2, 3 signals with different shapes in different in the scale, different chemical shift. Now, when you are determining the number of signals, it is important that we know if protons are of the same type, so homotopic or enantiotopic or diastereotopic. And point is that when protons are homotopic, meaning the same, they give the same signal. For example, this molecule, if you do a rotation axis here, these two are interchangeable. Here, if we do a rotation on this axis, these two exchange. Same thing here. So these are homotopic. And you may be asked questions, what type of protons are these or that? Another way that we do is we use the same replacement. So this is theoretical. We're replacing one H at a time by a deuterium, so the heavier isotope of hydrogen. And if you do that, these two molecules are identical because if I rotate this, you get the other. So it is the same compound. That's why we call those homotopic. And again, we'll have the same signal. Now, symmetry is important. Here you have two H's. And of course, that's not a chiral center, but if I change one of the H's by a deuterium, you have a pair of enantiomers replacing one or the other. Now, same case here, that's not a chiral center. This is the same molecule. Now, this is not a chiral center, but you will create one when you replace either hydrogen with a deuterium. Now, what is important is that enantiotopic protons and homotopic, they have the same chemical shift. So you count them as the same signal. And again, that is important when we're determining how many signals. Now, here in the molecule above, notice that what we have here, this is a chiral center. We have 4 different substituents at that carbon. Now, in this picture, we're doing another, say, exercise, theoretical exercise, replacing one of the H's by a chlorine, one or the other. When you do that, the chiral center on the right-hand side stays the same configuration, right? So same configuration in each, but you're creating a new chiral center, and this had the opposite configuration. So these two have opposite, right? Configuration. Because of that, E and F are related as diastereomers, and we call those H's diastereotopic. Important that these two will give different signals. So when you're counting the total amount of signals, it matters. Let's do the molecule that we have below and determine the number of signals. Here I'm doing first saying this is proton type A. I have another H here. I'm going to call that a B. I'm going to call that C, and I'm going to call that D. Now, these two are diastereotopic because being sieged to next to a chiral center, you will be creating two different diastereomers. Again, because the configuration of this center is staying the same, just as the example above. But this is changing, so you're creating diastereomers. So total number of signals, so B, C, D, E, F. And notice that the trick of changing H's by deuterium, if you did it here, you're not creating a chiral center because here you have three H's. So there's going to be homotopic. And again here, same thing, you have three H's. Is when you have two that you want to be able to differentiate whether they are homotopic, enantiotonic, or diastereotopic, so that you count them as different signals. Okay. Now, more examples of that. This molecule here has a plane of symmetry. So this mirrors that on that plane of symmetry, right? So they are chemically equivalent. Chemically means same chemical environment, we say, right? Surrounded by the same thing. And they're going to have the same chemical shift. Now, here in the other molecule, you have a chiral center. And if you did the deuterium replacement, if you put a D here, you're going to create one diastereomer because, again, the chiral center here is the same. But you can do the replacement on the other H. So you're going to create a pair of diastereomers, and they are not chemically equivalent. In other words, you can say this is, I'm going to put the H back, HA and HB. These two will have different chemical shift. So you count them as different signals. Counting signals here, by the way, you would say in this molecule, one signal here, this is one, proton signals. So call that A because, again, these are equivalent. These two is another signal. Here you don't have H's. This is C, C, and D, and D. And here you have more than that. These H's here are chemically equivalent in this molecule as this. And you don't have chiral centers, so they are homotopic. Here, this molecule, we have signal A and signal B, so this is A as well, and B, plane of symmetry here. So you will have signal A due to 6 protons total, 6 H's, and signal B is 4 H's. So 2 signals. Okay. Now, more examples about homotopic and counting signals. So in the molecule here above, I'm going to draw that without the H's. So this without the H's will be this, like that, much simpler. So that is a metal. So these are the three. Notice here you have simply drawn the H's. But what is important is that we have a chiral center here. So the two H's, F and C, produce a pair of diastereomers. So therefore, these two are diastereotopic, and they count them as different signals. Notice the metal here, this is one, so they call it A. So here you have B, that's another metal. That is another, so metal, metal, another metal here. So they call that A. There is an H here, right? And they have called that A, and you have two H's here. And these two are diastereotopic. Again, next to a chiral center. So F, M, C. For that reason. And again, it doesn't matter if you did the deuterium replacement of one of the H's here labeled A, you're not going to create a chiral center. Neither you create a chiral center if you replace one of the B, because you're still going to have, you don't have 4 differences. So the only place where you be creating a chiral center is here. And these two H's are diastereotopic. All right, so the molecule under this is just to show you that these two drawings are exactly the same molecule without the H's. This is what you have in the Hazy plane of symmetry. So you will say one signal A, B, M, B, and this is C, and C. So three type of H's in here. You don't have a chiral center, so that's why you have A, B, and C here. Remember that when you have cyclohexane, the interchange, the chair flip happens quickly at room temperature, so you don't have a distinction between axial and equatorial hydrogens, and you will see that only if the temperature is really low, like a negative 100 Celsius, I believe. Otherwise, you don't see that. But again, counting signal is very important that you determine when the H's are diastereotopics. Now, observe signals, regardless of the instrument that you use, we have normalized the chemical shift so that you divide always the frequency where you observe the signal over that of the instrument. So this number, notice, is the same for aromatic hydrogens, the same in 300 megahertz or in the 60 megahertz. That's why we can use those tables in pretty much any instrument. And remember, so this is your standard to mark the zero. Tetramethyl close to that is shielded. As you move to the left, you're deshielding. So upfield, downfield. Now, tables, you're going to have tables of that. So you have reference values. Metal is 0.9, 0.1 to 1, as you can see here. And methylene is 1.2. That's a reference. Again, you have the tables, but notice what is important to remember is the effect of electron withdrawing groups. The stronger the electron withdrawing group it is, the more deshielded is going to be the H's. So these H's are going to be deshielded compared to those in methane. But the most deshielding occurs here because fluorine is more electronegative. So check out those numbers. The other effect here is that the electron withdrawing effect here is additive. So one chlorine does that, moves it from 1 to 3.1. 2 chlorine moves it further down, and 3 further down. Okay, so, but again, this is knowing what electron withdrawing groups will do. This is a chart that you're going to have. What things that are probably easier to that we need to kind of see immediately. Aromatic between 7 and 8, that's something important. Alkyl, methyl and methylene, these are a higher field. Notice that upfield. And allylic, as you have here in the metal here, we consider like the phenyl ring as an electron withdrawing group. That's why these are lower field than the metal here. And again, here's the effect of electron withdrawing group, moving that up. The H of OH is this. H is, well, between 2 and 5. It also can be large or small or even invisible if you have proton exchange. Vinylic, notice aromatics between, say, 7 and 8, and these are a little lower. So that's important to remember. In two peaks that are very easy to spot on and identify are the aldehyde and the carboxylic acid, because that's at the most downfield possible. These two, so very distinct. Now here, again, predicting the number of signals. When you have a molecule, you want to predict the number of signals. So say, I'm going to do the drawing, say, as you will have it. Say on a test, maybe you will have this. Here you will have carbon and say Cl3. Well, let's do the one. Let's do this. You have two H's there, and here you have this. And what we need to see is that, okay, chiral center. And here I have two H's. That means that I create another chiral center here if I do the replacement. Therefore, the two H's here are diastereotopic. And that's why you count signal A, the three H's here. Signal B is, they put it like here, B and D, but nonetheless, we know that we have one here, and we know that we have these two are different because, again, doing the deuterium replacement, you will create a pair of diastereomers. That was important. So predicting the number of signals, you would say 1 in the HA. These two are two signals and one here. So you have 4 signals total. The other thing is that close to carbonyls, even though the numbers, it has like 1 ppm, for example, and here these H's are also going to be deshielded, but the more deshielded is going to be HC. So next to an O. And so HC feels the effect of the oxygen of the OH plus the carbonyl next to it. So it's going to be most deshielded. But the OH, again, remember, between 2 and 5, but depends whether we have an exchange or not. Okay, so this diamagnetic anisotropy is saying that protons in different positions of these molecules feel the external field different. Protons in benzene saying in the outside they will be deshielded. That's why they are here between 7 and 8, as you can see, and they are identical. In benzene, remember we call that also 6 aniline, and this right here, it's 14 aniline, saying the number of carbon atoms. And what is important is that the atoms in the middle feel now much less deshielded because of the lines here that we have on the magnetic field. So the point is that here you have two signals essentially, the ones that are deshielded in the outside and the ones that are shielded. So in the inside is negative 1 ppm. So that's what's different in these anulines. So again, different parts of the molecule feel different, the external field. That's what that is. Now this is the spectrum of ethyl benzene. And as you see here, these are 5 aromatic protons. Notice this region is complex. And you have an ethyl group. That's your ethyl pattern. And quickly, let's say, remember that here you have CH3, CH2. So the CH3, this C2 neighbors, so these guys are looking at N equal to 2 neighbors. So by the N plus 1, this is the triplet, right? N plus 1 rule. And now the methylines, which are these, they're looking at 3 neighbors, so N equal 3. That's why it is a quartet. And that's a typical ethyl pattern. So patterns that we need to remember. But point is grouping all of the aromatics in the same. They're not identical. And the fact that it's complex is because here you have, for example, say type A, B, and C because of symmetry. So A signal is due to 2 H's, and it is a doublet. As you can see, it is within 1, 2, 3 bonds, so couples to that. So it is a doublet. And proton side B, this is complex, so it will be doublet of doublet. And same here, so B is complex, C is complex. So that's why we see all that overlap in that region. Now these is naphthalene, and here notice that we have A, so that's one type. We have B and B, so 2 types of H's. So they feel different chemical environment, and that's why you have those 2 signals. H couples to B, they are within 3 bonds. So doublet, you probably, this is like a small, but you can see it's a doublet. And B also, so remember A couples to B, B couples to A, so this is a coupling constant, right? And J, B, A. So, and this should be the same. Point is that B, notice that B here, these two B's are the same. So they are homotopic. They do not split each other. So B fills only A. So that's a doublet. Okay. So moving on, this is anthracene, more complex. So three different type of aromatic H's. So let's label that A and A. And then we have B and B. And let's label that in green, and C and C. So three. Multiplicity is different. So notice type A, if we count bonds, 1, 2, 3, 4 bonds. So they're not coupled to anything. So no neighbors, meaning no neighbors, n plus 1 rule, that is a singlet. So H type A, this is 2 H's, and it is a singlet. Of course, in the aromatic region. So these guys are this. And then we have type B. Well, B actually is coupling. Let me do another color here. 1, 2, 3 bonds. So B couples to C. So it's going to be a doublet. And now these two are homotopic, so they don't call triangle. So when you have 2, it is equal intensity. When you have 3, it is like that. Yeah, I think it's Pascal triangle that. When you have 4 is 1, that, and so on. That is the patterns that you will see. And typically we use letters here like a D, a T, and a Q. But for down below, you're going to have to say quint and sext and sept to be able to differentiate. These guys, many cases, are not resolved, and so we call that M. So a multiplet. These are how they look like, what we did. And now we are doing some example of molecules. This molecule here is symmetrical, so it's 1,2 dichloroethane. So these two guys are the same as that. So all of those are equivalent. So homotopic, one signal. Very simple spectrum. So because they're homotopic, these do not split each other. So that's why you see only one signal. Now this is ethanol. And this here is the OH. The others is the ethyl pattern. So here you have CH3, CH2, OH. So these guys have 2 neighbors, so N equal 2. Therefore, this is a triplet. The CH2 here, this guy see 3 neighbors, so N equal 3. Therefore, is a quartet, and this is that, what we have here. All right, now another compound. Notice here what we have, I'm going to do a different drawing. 1, 2, 3, and same. So here what we see is 3 and 3 is 9 H's that are equivalent, homotopic with no neighbors. So that is a singlet, and this is what we have here. Now here we have a CH2, a methylene with no neighbors. Remember that we don't have H's here. So that's another singlet, but this is only 1 H, and again singlet. So very simple spectrum, that one here. So these 3 are the same. So 9 H's. No H here where I have the dot. And so here I have another type. So 2 types. Oh, yeah. Here is 2 H's, of course. There's only 1, 2 H's. And 9 H's of the other. Okay, so point is that now, given the structure, we can draw that. So if we're given a molecule like that, we should be able to do an approximate drawing or assign given different pictures of that. All right, so more examples. Here I have one simplified molecule. Well, this drawing could be even more like the line structure could be simply that. But what we're saying is here I don't have H's, so no signal. And here these three are equivalent, so I'm going to say A, A, A. Then we're going to have these two here, and these are, we don't have a chiral center. These two are going to be homotopic. Then I have another signal here. I have an H here, and these two are the same. So predicting the number of signals here. In about integration, well, these are 9 H's, these are 2 H's, these are 2 H's, 1, and this is 6 H's, the E-type multiplicity. These 9 H's see 2 neighbors, right? So 2 neighbors, so that's a triplet. Now, B is complex because it has, well, it doesn't have neighbors here, so it's not that bad. So it sees 2 neighbors, so it is a triplet as well. So 2 H's is triplet. C also is a triplet. There is no H's here and only on that side, so it's another triplet, right? And then here, this proton type, this is 6 neighbors. So this is accepted. In protons, the type E is 6, and it is a doublet. There shouldn't be a comma here. So that you can say is the number of signals. That would change if we had a chiral center somewhere, but do remember when you can have diastereotopic protons. Now let me make a different drawing here. Yeah. So now in this molecule, we have 2 H's here. But what I want you to see is that these 2 H's are not identical. They're also diastereotopic, because if you replace either this 2 with a D, you're going to create a different molecule, either the E or the Z. So pay attention that these 2 are diastereotopic. Again, the deuterium replacement will give you either the Z or the E. Therefore, they're going to be given different signals. All right. So counting signals and predicting integration and chemical shift, that's what we have been doing. So metal here, these are 3 H's. And now, I'm going to draw just one of them to count bonds, 1, 2, and 3. So this couple, that is a doublet. And now I'm going to do the easier ones first, but I'm going to say B, C, D, E, F. Now, going to the other end, F is 3 H's, and they're looking at 1 neighbor, so this is a doublet. This OH always shows as a singlet. Remember that it may disappear. D is complex because it couples to, what did I label that with C? These two couple, and the other coupling as well. So the signal is 1H. And on one end it has 1 proton, so it will be doublet of. And here you have 1, 2, and 3 bonds coupled to 3. So it's quartet or quartet of doublet. That could also mean a multiplet, simply. Depends. On these two, this is complex because this one right here labeled C couples to B. So that will be 1H. Coupling to B, it will be a doublet, but couples also to that, so doublet of doublet. So that is number of signals and multiplicity. Oh, I didn't do this one, so 1, 2, 3. B is complex. So due to the coupling with C, this is going to be a doublet. But because here you have 3, it's going to be a quartet. So same scenario, doublet quartet or quartet doublet. Either one. Okay, let's chemical shift here when we are predicting that. Remember that vinylic H's between 4 and 5 or so. Let's say 4 or 5 ppm, right? These guys, this is a metal, so baseline is 1. So from that, it may be shifted a little because it's next to an sp2. So I don't know, I'm going to say 1.5, but this is approx. What I'm saying is the baseline is 1, and from that, you're going to de-shield a little bit. These two will be separate, and again, complex signals. This guy between 2 and 5 is singlet. This is next to an O, so it's going to be maybe 2 ppm or so. Approx. Again, you will have the charts. We're here using an approximation or what that will do. And metal here, again, baseline is 1, but the next carbon is an O, so it's going to be moved downfield a little bit. But what I have drawn here like this, the number of H's, remember, is related to the integration. So number of H's that give that signal. Chemical shift, a number of signals. Remember when hydrogens can be that stereotopic of note. Notice that here in F, we don't have that stereotopic H's there. Because here you have 3, and if you have 1 replaced by deuterium, you're not creating a chiral center. Okay, so this is much more complex. So, but again, you may have given just a drawing with the skeleton, so not the H's. So your first step should be completing and adding all the H's. So you may see again this drawing like much more simplistic. I'm trying to draw in not that easy here, but that. And that will be 2 metals, and that's pretty much it. So if you see that, then you should be able to draw all the H's, which is what you have in the drawing. Now let's group. This is metal, metal, which is this. That is actually an isopropyl pattern, if you see that here. Isopropyl pattern is when you have protons type A, these are 6 H's, and they have 1 neighbor, so it is a doublet, part of the isopropyl pattern. And B is 1 H, and it has 6 neighbors, so it is a septet. So that is the typical isopropyl pattern. This is the vinylic region. These two are homotopic this time. And again, these are different chemical environment. Point is that we observe where they are surrounded by the same chemical environment. Is what we mean by that, which is electronic environment. So when you have these shielding groups, it means something is electron withdrawing. It removes electron density about that nucleus. Therefore, it moves downfield. Okay. So these are patterns that we want to be able to recognize. The tributyl here, if you see in this drawing, this is like, let's draw this, are 1, 2, and 3. 3 metals. Here you don't have any H's, so neighbor is 0. So that's why you see that as a singlet integrating for 9 H's. So 3, 3, and 3. The isopropyl, which I mentioned in the previous slide, so this you will see this pattern. So here's 6 H's, so 3 and 3 and 1 here. And that is a pattern. So the 6 H's are looking at 1 neighbor, so that's a doublet. But notice this is much larger. The real size for the septet is this. Remember that the other drawing is like zooming in. But this is like the real sizes. It's smaller because it's only 1 H. So that is a typical isopropyl pattern. So you guys want to remember those. And the ethyl that we have said previously more than one time. So here, 3 H's looking at 2 neighbors is a triplet. 2 H's in the methylene that are looking at 3 neighbors. So they become a quartet. And again, these numbers above is the integration. So how many H's give that signal? This is the pattern that we're saying. That's the ethyl. And important here to recognize when does an ethyl and when it's not. It is an ethyl when you see that the pattern triple quartet, but this distance here, JAB is equals BA. Same. If it's not an ethyl. It is in other parts of the molecule, let's say, but not necessarily connected. This is signals that might be resolved or not. Notice here signal A, that is methyl, and a little bit downfield, it shows as a triplet because it's next to hydrogens type B. So in these are 2, so that's why it's a triplet. The following here, methylene, notice is shielded by the chlorine and also next to a carbonyl. So that's type C. And what this is taken with a 300 megahertz. And this is a 60 megahertz. So what we're saying here is that simply the instrument that is not as powerful may not be able to resolve that. And so we may see signals on top of each other. Okay, so that is now examples going into that. In this molecule that we have here, para isopropyl benzaldehyde. So remember that European chain and aromatic compounds. We have here benzaldehyde in para isopropyl. But what we want to see here first, in the aromatic region, we have some symmetry. So this product is the same as that, and then you have B. What it says is that we have 2 types of H's in the aromatic region. And not only that, A couples to B, so that's a doublet, and B couples to A. So 2 doublets. This pattern is characteristic of a disubstituted benzene ring. That's it. The other pattern that we have here is what we discussed in the previous slide. That is the isopropyl pattern. So here, remember that in the isopropyl, you have an H here. And that pattern is the doublet septet that we have here. But again, you want to remember that a para disubstituted aromatic compounds give that pattern, doublet. And that is important when we're predicting. Now here's another pattern, para substituted. And what we have here is, that is in the aromatic region, so we're going to say A, B couples to A, so only one neighbor. That's why it is a doublet, neighbor equal 1. That is just the zoom in. And the other signal here is just this H of that. Because remember, this is proton NMR, not carbon. All right. Here, again, another pattern. If you see, this is only the molecular formula. But what we see here in the zoom is like the pattern 2 doublets. So when you're solving that structure and you see these 2 doublets in the aromatic region, you immediately think of a disubstituted, a para disubstituted. And next step, all you need to do is put the bromine and the chlorine once you recognize that pattern. So that's easy to solve that structure. Here, now we have a more complex thing. We have 9 H's here, but we still have, this is going to be split, but what we have here, let's do the HDI first. 1/2 of twice the number of carbons, so that's 20 plus 2 minus 13 minus 1 because I have 1 bromine. So I'm going to have here 22, 1/2, and this is 22 minus 14, That's 8 over 2. That's 4 unsaturations, right? 4 unsaturations. When you have these many carbons, remember, it is almost always that's a benzene ring. The other thing is that we see these patterns, so it's likely to be disubstituted in pair. Now, one of them is the bromine. And here I have used 6 H's, so still need 4 more. And this is here, very large. These are 9 H's, so it's already giving me that this is a third butyl. That's why. Okay, so now here we have H9, C9H12. So again, what? Oh, I didn't want to do that. I touched it. Too bad. I skipped that. Well, now let's talk about the molecule that we have on the screen. So here you have label. Again, remember that you may simply have a drawing that's much easier than that. So these two, and here you will have this. And that's about it. So we need to draw the H's. So your first step should be drawing your H's if we have a structure like that. And remember that these two are diastereotopic. They're different because if you replace either one with deuterium, you're going to get the E or the Z. Remember, that's a metal. So these two are the same. Notice they are homotopic. You don't have a chiral center. And here, these two again, different. Okay. Moving on here. So how you can identify this molecule. So quickly, looking at what is the answer here, what describes that. This here is 2 H's, right? And they say 2 neighbors, so that is a triplet. Next to an oxygen, so that's likely around 4 ppm or so, roughly. I'm going to do the other here. Next to that is 2 H's. And close to a carbonyl, so I'm going to say at about 2 ppm. This again, I'm approx. You have the charts. So now, oh, what did I say? It is a triplet. 2 H's triplet. And now this one here is complex, couples to that. Here in the answers, notice that it says quintet. So it's adding 2 and 2, 4 to give a 5. So this, you should predict like this is 2 H's and it's quintet. Because there's no option like double, triple, not such an option. So that is that. In this one, we'll also have 2 neighbors here, 2 neighbors here, so it's 4. Another quintet. So 2 H's quintet. So I'm going to be looking at these two that are very distinct. So 2 H's triplet, 4 ppm. What is that? 2 H's triplet, 4 ppm. And the other triplet, so that's the answer right here. You see that? So what I was looking is at these 2 triplets that are much easier. So I always go for the easier part to identify. Let's see. This molecule looks fairly complex. However, it has a lot of symmetry. So I'm going to divide this screen in 2. So I'm going to say A. These are 2 H's, no neighbors, so singlet. Well, 2 H's, no, 4 H's actually, because I'm adding 2 and 2. So that's the signal here, right, is identical to that. So at the end of the day, B is also 4 H's. And they're looking at 2 neighbors here. I'm going to call those C. So this is a triplet. Then I'm going to be looking at what matches here. C, notice that I'm going to put that in red. No H's here. No H's here. So C, looking at only 2 neighbors in B. So there's 4 of those. So 4 H's, right? And that is a triplet. So we have identified A, B, and C. This are the same, so we're going to call those D. And here we have 6 and 6. This is 12 H's total, this side and the other side. And do we have neighbors? We don't. So that is a singlet. 12 H's. Lastly, we have this one, and that is the aldehyde. Beautiful thing is that this is close to 10 ppm, and that is always, this is 2 H's, and is a singlet, and we know that this is next to 10 ppm. With that, we should be able to pick the answer here. So here I have, this is 2 H's singlet, so 2 H's singlet, that, and I should have the other thing that is very distinct is 12 H's singlet. 12 H's singlet, I have those 3. Okay, it's got to be the first one. You probably see that because it's 2 H's in the aldehyde region. So we have one on each end of the molecule. This two, let's say, these two options, 4 H's triplet. This is in 4 ppm. This is either, this is 4H triplet, 4H triplet. The one that is 4.7 ppm is the one that's closest to the O, and the other is closer to the other region. But when you're deciding in all of these answers, it's gotta be the one that has 2 H's type of aldehyde in singlet. So you are in between these two, but here this is saying 6 H's on that, so you cross that out. So this is the first one. Here, this is using NMR to identify between these two. So here we have just deciding how many signals. I'm going to say there is a plane of symmetry here. So A, no, H is here, B, C, so 3 signals. Here you have A, B, and everything is different. A, B, C, D, E, F. So the answer to that, I should have one that says 3 signals in the first. Where is that? 3 signals and 6, so that's that. Okay, so when you're doing questions like that, here, this is 9 here, and this at about 4 ppm. So next to an O. Unfortunately, I'm touching the board. But anyways, sorry about that. But let's go for that. I shouldn't have the keyboard so close to me. Okay, so here is the number of signals. So let's do that. That's definitely 1, right? But then in the aromatic region, I will have B, and these are different, C, D, E. So I have 5. Here, this is a para disubstituted. So you have, if you have A here, then you will have B, B, C, and C. So only 3. So 5 versus 3. Right? So here you have a plane of symmetry. So these two are the same. These two are the same. And then the other. So 3 versus 5. So your answer is the first will have. Oh my God, I did something bad. No, that's okay. With the, so 5, and where is that? 5 and 3. So that. Here again, this is number of signals. Here I have A, that has a plane of symmetry here. A, and B. Some of those only 2 signals. Here I have a number of signals. These 2 metals are different. And here I have an H. And here I also have an H. So I'm going to have A, B, C, and D. That many. So that's what you need to be doing when you're answering this question. So 2, and then the other has 4. this one. Okay, moving on. Here, that is easier. All of the H's here are identical, right? And that is one signal, right? Here you have an H here. So here you will have A, and B. So two signals. And you can also recognize the plane symmetry or rotation. Point is that all of those are equivalent, okay? And here you have three metals, the same. So here you expect two signals, one integrating for 9 H's and the other for 1 only. Okay, so what was that option? First compound, one signal, and the other will have 3, no, 2. This. One signal, and the other will have 2, so that. Okay, now moving on, let's do these spectrums. So C8, H10, so let's do the HDI is 1/2. And this is 16, right? Plus 2 minus 10. O doesn't count, so 18 minus 10 is 8. So that's 4 in saturation. So I already know that I'm putting fragments here together. I will have some like that. Something like that. And this is complex. So I'm not expecting a para substitute or anything like that. But I have here my ethyl pattern. Actually, if you see this here, that's 3. And let's do the integration here. These are about same integration values. So if you have the same integration values, means the same number of protons. So that's probably in an OH. If this is the case, and these are 2 triplets. When you have 2 triplets, think of this. X and Y. So here, this signal will be a triplet because it has 2 neighbors, and this will also be a triplet. So I'm looking at that. And this is likely, because I have an oxygen, this is likely to be an OH. So putting those pieces together, these pattern, this and that, my compound is the following. This. Okay. Okay. Now here, what do we have? C7. So you start here as always. HDI 1/2. 14 is 2 twice the C plus 2 minus 14. So here, what do we have? This without, so only 1 unsaturation. Maybe a carbonyl, but we don't know so far. But what we see here is a pattern that we know. So, and I'm going to draw that. Whatever X is here, if this is an H, A, and B, that is the isopropyl pattern. And now the other thing that I have is that this is much larger than that, which makes sense. Those are adding up. The other thing is that I need to make a molecule that has an oxygen and that has isopropyl patterns. So, and I have 1 unsaturation. It cannot be an ether, guys, because I don't have an unsaturation. And here I have 6 carbons and I need 7, so I'm going to cross that, but the change is really simple. So if I add this is my molecule. So the 2 isopropyl pattern, and now the count is 7 carbons and 1 saturation. Okay. Here, see the pattern here, doublet, that means para disubstitute benzene, X, Y. This is 9 H's. So this is likely a tributyl when we have that. And this is, I'm going to say this is a tributyl. So notice that I'm putting like pieces together. This is because of the pattern that I see in the aromatic region. And this is because of that. I know that's a pattern for tributyl. So this is 6. If tributyl has 4 carbons, it matches. Tributyl is 4 carbons. This is 6. So have the carbons. It matches that. And I need to know, so my guess is that is no H. It is within the range. And it's small, which makes sense if we have an interchange. So I'm going to draw my molecule as a tributyl. I know it's pair substituted. So that is my molecule. Okay. More down. That's more complex. However, let's see what I want you to see is these numbers. So this is like 1 to 1 to 1 or 2 to 2 to 2 in the number of H's, and here I have 6. So that's the amount. So I need to make a molecule that will have this CH2, CH2, CH2. And yes, one of them, let's say that I put X and Y. This is a triplet. So that'll be a triplet, right? That will be a triplet, and that is complex. So which I see triplet, triplet, and one signal is more complex. And now when I do my HDI, putting my pieces together, that's one piece that I see. HDI is 1/2 of, that's 8 plus 2 minus 6. So 10 minus 6, that is 4. And divided by 2 is 2. 2 unsaturation. So I don't have an IR data, but I need to put 2 unsaturations and 1 oxygen. So into half to CH2, CH2 and 2 oxygens. Say that I do CH2, CH2O, CH2, but I need another carbon, and I need another carbon and an oxygen. So I'm gonna come up with this to complete the number of carbons and the number of oxygens in 2 unsaturations. 1 is due to a double bond and 1 is due to the ring. So that is lactone, and it's butyryl lactone. But point is that I started with 3 CH2s. Here. What do we have? HDI. Again, things could be easier if you had in the previous problem, if you had the IR, you would see the carbon. But here we didn't have that data. We're working only with this. So HDI here is 1/2, and this is 18 plus 2 plus 2 minus 10. So this is 1/2, and this is 20. Minus 10 is 10, is 5 unsaturations. Okay. 5 unsaturations could be a carbonyl, could be a ring, but an aromatic ring, I know it has 4, so I can start there. And I can have a carbonyl and that make 2, but I don't know yet, but I'm proposing that because I have an oxygen. And only I don't see anything here, apparently, right? And if I add this 2, I have my 2 unsaturations. That's why. And here, let's see, integration-wise, this pattern, let me see. This looks like a triplet quartet. And if this is true, these 2 are an ethyl. That will make sense with the integration. This is larger than that, so the CH3. So this looks like CH3, CH2. So if I have that and I have these 2 elements, I'm going to put it together the following way. I'm going to put this down one side, and on the other side, I'm going to have this. And that matches that structure. Um, but in some problems, you may have more than one possible answer. But here it was obvious that it was an ethyl, so not any ketone. Okay, that is a C5. So C5H12. That doesn't have unsaturations. Let me see, because regular alkanes are CnH2n plus 2, and this is what we have here. You can do the math as well, but HDI is 0. So now I need to build something with that. What I have here is something like large. So it might be, I'm going to think on an isopropyl pattern, because I have an H here, and that will be, yep, here I have, let me see, not that. Okay, to be that a singlet, 2 H's, if I do the math here, this will be like 1, 2, 2, 2, would that be 3? Maybe, I think, and 4, or double that. Maybe we can do the math to that, but it's roughly that. So when we have that, the structure that matches this, and maybe, let me see, to have this, here we will have 3 and 3, so that'll be 6. And OH, these two are going to show up as a doublet down 6. So if this is 6, that makes sense because it's 6. Right, so that will be the structure of that. I'm going to have to move a little bit faster though to do these. Here, this is matching with the structures. So what I have here, this one looks like an alcohol. So that's not an alcohol, so I'm crossing this too. Next, what I see here is 6 H's. So that are equivalent. So in the only molecule that has 6 H's that are equivalent is that one. Next is the ethyl pattern. So the triple quartet. This is these two. Is the ethyl. Okay. Moving on. Here. This is just a zoom in of that, but what we see here is essentially 3 signals, 3 blocks here. So predicting the number of signals, if you see this one, this only give you 1 signal. That can be. And here you have A, B, C, D. That also not the answer. Here you will have 1 H here, and so A, B, B, C. Well, that could be because we have 3 signals. So and then we're going to analyze that. So A, B, C, D, just by the number of signals is that one. Then you can analyze whether the multiplicity matches. Here I have this too. When you see the ppms, these are in the vinylic region. So these are 2 H's attached to sp2 carbons. So here I have only 1. So that can be. Here I have 3. That's also not it. Here I have only 1, so not. And here I have 2, but these are kind of very similar. The answer to the problem is these 2, which are actually diastereotopics. They are different. They look different side, but you may be in between those 2 being different. But this one, let's see if the other portion, this will be a triplet. 1, 2, 3. A triplet. Do I have a triplet? I don't. So that between these 2, Again, let's do it again. This signal is 2 H's and it's a triplet. I don't see that over there. So my answer is this one. Okay. All right, so that's the structure to repels here. It says that's the molecular formula. So HDI, and it's interesting because this is only 2 signals in 2 singlets. Very interesting. So I did the math here because that's the relative integration. One is in 3.9 ppm and the other in 8. So that's one 8.1. This is aromatic. And this looks like close to an oxygen or something like that. So now I need to ensemble that. I have an aliphatic region and an aromatic region. Let's do this. HDI is 1/2. This is 20 plus 2 minus 10. So 10 that's 12, that's 6. And so with 6 unsaturations, in only 2 signals, now I need to come up with this. So 1 benzene ring, and I have 4 oxygens. So I'm gonna start there. That's 4 unsaturations. Because I have 4 oxygens, I can think of ketones. By having 2, I can think of carboxylic acid, or I can think of esters. If I have a carboxylic acid, the problem probably should tell me that I have an extra signal, and only one for that. But by the integration here, relative integration is 4 to 6, meaning that I have 4 to 6. So if I have a disubstituted benzene ring, for example, and to have 2 signals, it only can be 1 in the aromatic region and 1 in the other part. So it needs to be a para substituted so that I have 1 in the aromatic region, 1 signal. Means it's this pattern. Then I will have 4 H's, so that's good, 4 H's. And then I'm going to ensemble the other part. And I need 6 carbon. I'm going to do this because I need to match the number of carbon. Let me see if that matches. Only one metal here. CH3, CH3. So I will have 6, 8, 10 carbon. That matches. But notice, I did that because there's only 1 signal in the aromatic region, and there's a lot of symmetry in 1 in the aliphatic. And this is at about 4 ppm because it's next to an O. Boy. Now I'm gonna go quicker. I mean, this lecture is long. So about carbon NMR, remember that here we count types of carbon. So here, this molecule, I have it. So A is got symmetry, so only 2 types, right? Butane here, again, symmetry, but you have 1 in the center, so 3. These 2 are the same, so 2 signals. 2 signals. Here, 1, 2, and 3 more, so it's 5 signals. Again, look for plane symmetry. The more symmetry there is, the fewer the signals. That's what it is. And we will see the same effects as shielding and deshielding. So here, the number of lines, you're going to see decoupled spectrums, so just simple lines. Here, number of signals in carbon. In protons, you have only 2. So A and B, but now you have this. So I'm going to say A, B, B, and C. So 3 signals in proton and NMR. Here, in carbon, I'm sorry, this is carbon. So 1 type here, 2, 3, 4. This is carbon. So I'm going to label those. So 1, 2, 3, 4, 5. Here I'm going to start anywhere you start is fine. C1, C2, C3. This molecule doesn't have symmetry. You have here the substituent, so we need to pay attention to that. So 1, 2, 3, 4, 5, 6, 7, 8, and they're all different, carbon NMR. All right, this one here, ethyl acetate. That's the formula, ethyl acetate. So you have the table of chemical shifts. Carbonyls are the lowest field, always be close to 200 ppm. So that is a carbonyl right here. In similar to the other spectroscopy, carbonyl closes the shielding. So the metal C1 is at a lower field than metal C4, which is that this is 77 ppm, deuterated chloroform. And higher field is C4 and then C2 because it's next to an oxygen. Same thing we did in proton. This now you can use proton and carbon NMR to distinguish constitutional isomers. These are isomers of dimethylbenzene, this is the 1,2 pattern, so the ortho, that's orthosilene. This is 1, 2, 3, so that's the metasilene. And that's 1, 2, 3, and 4. That's the parasilene. Well, here you have the proton NMR type in red. So, but I'm going to just put letters here, probably easier. So, A, B, C, C. And you can see planar symmetry here. AC, right? And this. So you can distinguish that. Now, here, this molecule, you do have a planar symmetry here. So these two are the same. And these two are the same, but here you have this is different to that, so it's for signals. And in para, remember that what we said that para that is substituted, that's the simplest pattern in the automatic region. But this is even simpler because you have a plane here and a plane here, so you only have two signals. But if it is X and Y, like in the previous examples that I showed you, then you will have two signals. Two doublets. This is doublet, doublet. That's a pattern for that. This is carbon. Remember, this is type of carbon. So you have, again, planar symmetry. So A, B, B, C, C, D, D. And that is the ortho. So again, you can use, you may be asked, how do you distinguish these molecules using IR or using NMR or using carbon? So that is the idea, identifying the number of signals. That table you will have, so noticing where are the bands. But again, it's very similar to proton. These are the most shielded, but anything like oxygen or nitrogen will move it downfield. And this is alkenes and aromatic, somewhat similar to protons. And these are the very mostly shielded portion of the spectrum. This is more like that here, carbonyls. All of those are carbonyls. And these are true. So notice this is more de-shielded due to the electron withdrawing effect. Oxygen is more electronegative than nitrogen. That's what you will see here. I'm gonna skip that. That is a means again. Where are the carbons? Depending on they have an electron withdrawing group, so they're gonna be affected by that, and nitro as well. Here, this problems like that could be simply say, what is the expected number of signals? So I'm gonna do this. So A, B, this is carbon. So I'm gonna say C, C, D, D, A. Here, A, B, C, planar symmetry, D, D, E, E, F. Here, everything is going to be different now. A, B, C, D, E, F, G, H, I. A lot. But this has a lot of symmetry. So one signal only. This is the pair that is substituted. So in the ring, A, B, B, but then it has C, D, because they are different, E, F, G. And what you can do all of those, but A, C, B, C, these two are the same, so D, E, E. This has a lot of symmetry as well. This is only two signals, A, B, and B. Here, A, B, C, D, E. Okay, what else? This is bromobenzene, so this is CHCl3, so impurity in deuterated chloroform. And this is all of the aromatic region, they are different. So one is this one, these two are the same, these two are the same, and whatnot. So monosubstituted benzene green. This has the ethyl, which is, this is 0, that's your TMS. These two are the ethyl here. And then you will have in the aromatic region, remember this is the para pattern, so these two the same, these two are the same. And this is different to that. So that's why in the aromatic region you have 4 signals. And last one here. So what spectrum matches here? Notice this is carbon, but it's also giving you, when you do depth, the coupling techniques, you can determine which of these signals are due to CH2, CH3, and CHs. We call, when it's C only, it means it's tetrasubstituted. We'll call that quaternary carbon. When it is a CH, so depending using depth techniques, you determine that. So what we're looking at here is a molecule that has 3 metal groups that are different. 3 types of metal group. In this C, so with no H's, 2 quaternary carbons. That's your deuterated chloroform. That in fact is just a solvent, so we don't take that into account. This molecule, I'm gonna say it quick, is the one that matches because this 3 is 1 and this is this large one. Large integration. The other 2 metals are these 2. So this is, one is this and one is the other. And here you have carbon, carbon, and carbon. The carbon here is quaternary, meaning it's one of these C's. But it's this because this one is in the alkene type region. So this is like 130 ppm. And this is the one like in 30 some ppm. I don't know, I'm gonna say 33, just can see very well the scale. So, and that's how you would assign that. And this is ACH, obviously. This is this H. Okay, so with that, we have finished the review of NMR. I know it's long, but you can pause the video, of course, go faster or repeat a part when you need more help. All right, that's all for now.